Okay, our next speaker is Dr. Abigail Fraeman, the Deputy Project Scientist. Welcome to the Mars Society. Come on up.
Wonderful. Thank you. Great. Thank you so much for inviting me to come speak to you all. I'm really excited to be here. I realized I didn't finish writing the title. I'm actually the Deputy Project Scientist for Curiosity, which is a very similar looking rover. But today I will be talking to you about the Mars Curiosity Rover and just showing you some of the things that we've seen looking at Mars over the last 13 years. I have to start off with what we saw yesterday morning when we came into work and we all had to plan what to do over the weekend. This is where Curiosity is currently parked. We're looking at some really interesting rocks that we're calling the boxwork structures. And let's see if I can pull up a laser pointer here. The boxwork structures, and we call them that because they look like kind of boxes. And it's the series of ridges and hollows that we're investigating, trying to understand what were the processes that formed these different ridges and hollows. We think groundwater was probably involved, and we're wondering, was it a process where water came up and formed some sort of cement in here? What was the kind of water that was involved? Was it really salty? What was the temperature? Was it something that was long-lived? Did it happen very quickly? How did that affect the rocks? And so we've been having just a wonderful time exploring these sweet enigmatic features. At the moment, we're looking for a place to hopefully collect some rock samples to put into the explored laboratories on Curiosity. And so we planned a little bit of a bump into one of these hollows that we'll be doing over the weekend. When we come in on Monday, hopefully there'll be a piece of rock. There's already rocks in the hollows, but there's one little one right over there. So hoping something like that will be in front of the rover, and we're going to set us up and hopefully drill next week or the week after to figure out what they're made of. But before I get too far, let me jump back and show another image from Curiosity. And this, of course, was the image that we saw over 13 years ago when the rover landed at a site called the Gale Crater. It's a bit messy in this image. What this actually is an image from the HAZ-CAM on the rover. That's the camera underneath the belly of the rover that we use to see hazards as we drive. And when we landed, we picked up a whole bunch of dust and rock that got on top of the lens. And so good thing we built in a dust cover, flipped that dust cover off. And this was the view from landing 13 years ago. Couple things that you should notice. Of course, the shot of the rover, I think, just looks really cool. But really importantly in the distance was our targeted exploration. This is a mountain named Mount Sharp. It is 3 miles tall, or 5 kilometers tall, if you like metric. And this is what Mount Sharp looks like from orbit. It is in a giant crater called Gale Crater. That's about 150 kilometers across. It's right on the equator of Mars and what we call a hemispheric dichotomy between the ancient southern islands and the slightly younger northern lowlands. And what's really remarkable is this mountain in the center of the crater. The mountain is actually composed of a bunch of sedimentary rock that were brought into the crater and filled the crater up. And the goal of the mission was to be able to land at the base of this mountain and read these sedimentary rock layers as we climbed higher and higher. And by doing so, it's like reading a strip chart of Martian history. Kind of like if you were to go to the bottom of the Grand Canyon and then hike your way up, you'd be seeing many, many years of Earth's history and the different processes that were going on that formed those layers. And so we wanted to understand what those processes were and what that tells us about the history and the habitability of Mars. So that's what we've been doing for the last 13 years, is climbing this mountain. This is another view of Mount Sharp, again, from our landing location, but this is now taken with our color mass camera on top of the rover. Obviously, you can now see the mountain in the distance, some other cool things to see. I love this image because it shows how we landed on Mars using the Sky Crane system, which is this kind of inverted jetpack that lowered us to the system. And these are the impingement plumes of where we had the thrusters interacting with the surface. When we started driving, the wheel tracks just started like they came out of nowhere. So I love thinking about that. But if you zoom in, this is really the first look with our telephoto 100 millimeter lens on our mass camera. And it's remarkable that you can see the layers and layers and layers that we saw from orbit. And here we're starting to see them now from the ground and resolve them even more closely. besides just having layers, we could tell from orbit that the layers were made of different compositions, which was another clue that we'd be able to see this really dynamic history of Mars as we climbed our way up through them. And so I've labeled some of them here. Of course, the crater plains that we landed on top of. There was a big dune field right at the base of the mountain that we actually had to spend about 2 years sorting around before we actually got to the base of Mount Sharp. And then moving higher up, there's a unit with a mineral called hematite, which is an iron oxide that usually forms in the presence of water. There was a clay-bearing unit, which we could see from orbit. We could map that there were clay minerals associated with these rocks. Those are usually minerals that form in water and usually kind of pH neutral water. And then moving even higher up, we could see the kind of butte and mesa forming layers. This is a sulfate bearing unit or a salty unit. And we're seeing this transition now from clay minerals to salty minerals. And I'm going to talk a little bit more about that in a few slides, but it's an important potential transition in the history of Mars climate. We're now all the way to Urish. So we've been making our way up, reading all these layers. We're deep into the salty unit now, investigating those boxwork structures all the way over here. Another remarkable thing about this mound is that we can estimate how old it is. And in addition to the minerals that we see, we can also see that it should have formed at about the time that we think Mars was undergoing this dramatic climate change. So 4.5 billion years ago, we don't totally know what Martian climate was like. We think there was at least more water on the surface. And then, of course, now today, we know Mars is very, very dry and cold. And then we know there was something really interesting that happened about 3.5 billion years ago that caused Mars's climate to go through some big changes. And so by going to this particular strip recorder of Martian history in this section, we were able to see, what were the environments that were associated with these climate changes and how did that affect the potential habitability of the planet. Curiosity itself is our kind of Mini Cooper-sized rover. It has 10 scientific instruments that are designed to interrogate the geology and the environment of the area at Mount Sharp. I'll just point out a couple of the they're all really important ones, but the ones that drove the rover to be as big as it is are these 2 laboratories we have on board. That's why we call Curiosity. It's also the Mars Science Laboratory. It really is a mobile chemical laboratory that we have on the surface of Mars that is able to measure the composition of the rocks, understand their definitive mineralogy, what minerals are there, the crystal structures that are there. That's the instrument called ChemIn. And then there's also an instrument called SAM, which is able to detect volatile compounds in the rocks, things like water, things like carbon-bearing organic molecules, and make measurements of things like the isotopic composition of the rocks and the atmosphere as well. To get rocks into these laboratories, we need, of course, a drill that will drill into the rocks, create a powdered rock sample. That's what we're going to be doing hopefully next week, is getting more information about the composition of these rocks. This is Curiosity's journey. Yesterday, we planned sols 4,686 to 4,689. This audience is probably familiar, but a sol is a Martian day, a little bit longer than an Earth day. We have driven over 36 kilometers. So if you do miles, it's a little over 22 miles. The really important statistic for this particular mission is how far in elevation we've climbed, how high up the mountain we are. And that's over 900 meters in elevation. So we've made it quite a ways up to the top of this mountain, although for the 5 kilometer tall mountain, we have quite a ways to go to get to the top. But starting off, we'll just show you a couple pictures, of almost ancient history at this point about what it was like when we landed in an area called Bradbury Landing and then made our way actually in the opposite direction of Mount Sharp to a location called Yellowknife Bay, which was a specific location we could see from orbit. We thought if there ever was a lake here that was bringing in sediments and building up the lower part of the mound, that's where the lake would be. And so we drove there, and this is the beautiful site that we saw. And what we found back on Sol 166 of the mission, or back in January 2013, was indeed these rocks had all the characteristics of being lake deposits. They were very fine-grained. They had clay minerals in them, which is what you might expect to be deposited in a lake. And super importantly, one of the things that we found were the presence of carbon-bearing molecules, organic molecules that were trapped and preserved in this lake. And that was something that we found relatively early on. Although 13 years later, we're still making discoveries from the samples that we collected here. Because we have these wonderful onboard chemical laboratories, we're able to work with them and make experiments and change parameters in the way that we analyze samples. And we knew the site was really important. And so what we actually did was we called it doggy bagging the samples, where we stored some of the samples in the reaction cups in the instrument to save for future analysis. We were able to go back to our laboratories on Earth. We were able to tune how we run experiments on the rover, how we measure the chemicals in here. And a few years ago, did another experiment with the samples. And what we found increased our knowledge of the kinds of organic materials that were here. So this is the only slide I have with words. But just going through, this was a result that came out earlier this year. And I think it's remarkable that we're having kind of top 10 mission results coming out now from samples that we collected 13, 12 years ago. But what we found preserved in these lacustrine mudstones was not only just simple organic molecules, which is what we first reported, but we also started to find more and more complex organic molecules, bigger and bigger molecules. And what was recently reported was present in these long chain hydrocarbon molecules, which are basically anything with carbon and hydrogen. And these are some of the biggest and the most complex organic molecules that we found on Mars to date. And we don't know what made these molecules, whether it was biology or they were delivered from outer space or they were part of the interior composition of Mars. But what is remarkable is that this shows us that Mars has the ability to preserve these potentially important evidence of life or the building blocks of life in its rock record, even in rocks that are billions of years old. They haven't been destroyed by the radiation and the really harsh environments on Mars. So when we're thinking about the search for life on Mars, we can be excited about the fact that there may still be this evidence and all of this information still present in the rock records. I just love this picture. This is our current collection of drilled samples. There's actually 43 drilled samples, but 42 makes a better grid. So that's what I'm showing here. But these are all 42 of the drilled samples that we've collected over the last 13 years of the mission. This is remarkable because it shows you just how diverse Mars is. It's not just the red planet, but when you drill beneath the surface and you look beneath, you see Mars is the green planet and the gray planet and the purple planet and the brown planet. And all of these different colors are related to the different compositions of the rocks, which is related to their unique history, how they were in place, and then what happened to them in the billions of years after they became rock. But I'm going to move on now and just talk about kind of what we've been doing in the last 5 years or so. We made our way up most of the mountain. We found a lot more information about the presence of lakes that were filling this crater, and then also a really complex history of groundwater that then came in after the lakes. But I'm going to move all the way up, and I'm going to bring back that idea about this transition from clay lake minerals to salty salts called sulfates. And this is an area we explored back in March 2021. We started our exploration back then on Sol 3048, called the clay sulfate transition. And this is a particularly awesome image because I think it shows the transition really clearly. We can see it from orbit, but it was super obvious from the ground too. So all of these tan rocks in the foreground, this is really the top of what we call the clay-bearing rock section. And then moving up here, this is where we start to see the sulfate unit, these salty rocks. And you can see not only do they have a very different composition, but they have a very different expression of how the rocks look. And so a big question that we wanted to understand was why? What caused this change? What kind of environments did it reflect in Mars? Was this a one-time thing? Like, did the lakes disappear and then Mars just became really dry and salty? Was this something that was a more punctuated event? And so by exploring these rocks over the last 4 years, we've been able to answer that question. But before I get into that, this was just a nice image to bring up another point here. So this feature here, it's just a very photogenic mountain. We called it Mont Mercou. We were in an area where we were naming all of the rocks after the Nontron region of France, which is the type locality for a clay called nontronite, which is the kind of clay we found in the clay-bearing unit. But if you take a look at this beautiful Mont Mercou, this is another image we took when we were parked at the base of the cliffs, looking at what all the rock layers were telling us about how it formed. But this is an image we took right after sunset in the wintertime. And this represents another amazing discovery of Curiosity, and something I don't want to forget as I talk about the rocks. The rover has also been making these measurements of the Martian environment for the last 13 Earth years, or as of it was 1 a.m. UT on Monday, we just passed our 7 full Mars years mark. So we now have a record of 7 Mars years of climatology that we've collected with Curiosity. It's the longest climatology record. The only mission that's lived longer on the surface was the Opportunity rover. But with Curiosity, what we've done for the last 7 Mars years is collected a nearly continuous record of the temperature, the pressure, and the relative humidity every hour with our REMS instrument. And so it's this wonderful, complete picture that we're learning all about the Martian environment. We made discoveries like these clouds that come out during a certain time of year, these noctilucent clouds. They're made of CO2. We were able to look at the colors of the clouds to understand the grain sizes and how they formed. And I think this is just a beautiful picture, because when I think about going to Mars, this is a place I could see myself setting up my tents and just lying out, looking up at these beautiful clouds being lit by the sun because they're so high up, even after the sun has set. This is just another awesome cloud picture. We took this one in the last noctilucent cloud season back in February 23. These are these crepuscular rays, which are like these God rays, you might call them. If you're a photographer, this makes awesome photographs, and just so cool to the first time see this happening on Mars. To me, images like this really make it feel like a place, because it are these kind of Earth-like phenomenon that I really relate to. But let's go back to the sulfate unit. This is an image as we made our way up. This is an area called Paraitapui Pass. This was now when we were naming rocks after the Roraima area, where these really cool buttes called tapuis in Brazil. And this is just a wonderful example of the way the topography has changed, how we're seeing these giant buttes that are now towering above the rover. They made it tricky for us to work out our comm. It turns out if you're parked next to a giant mound of rock, it can sometimes be hard to see the orbiters passing overhead, that you need to relay your data. So we had to be very careful as we planned our path. But they were great for geologists, because they give us this amazing view of kind of the strip chart of the layers and really help us understand the structures. And what we were able to find out is that most of these rocks have structures that are indicative of being deposited in a wind-blown, sandy environment. So things like dunes and sand sheets and ripples, those are all the kinds of structures that we were seeing. So this is telling us that, yes, Mars is having this drying out period. The lakes are going away. But what about the salts? This was a cool thing that we found as we were driving up through. We also started to see some really interesting, they're called diagenetic features, features that formed in the rock, usually by groundwater. The blueberries that Opportunity found that are so famous are another example. But here we're seeing these kind of golf ball size kind of nodules in the rock, and they were really dramatic, really interesting. And because we're on a one-ton rover, we were able to actually drive over them and crush them open and make measurements of their chemistry. And what we found was that these nodules were the carrier of some of the salts that we saw from orbit. So that was a really interesting finding, and something that you really need to be on the ground to be able to figure out. We're going to keep moving our way up the mound now, and I'm going to take this box that's shown in black and just zoom in here and give you a slightly different perspective, just because it's easier to show all the details. Here again is bottom of the clay-bearing unit as we make our way up through to the magnesium sulfate-bearing unit. That Paraitapui Pass that I showed was this area right here. And this is just another image I'll show. We were parked about here looking right up the mountain. And this was the view we got. And this was one of the first view we got to the channel that we were about to drive up. And this is just another amazing picture we took back in November 2022. It's one of my favorite images of the mission. I have it printed out really big in the hallway across from my office. But it just shows all these amazing layers and layers and layers of history that we're going to be able to access on Mount Sharp. And then even higher up, really cool parts of the way tippy top of the mountain that are formed in a totally different way that we don't know anything about at this point. But as we made our way up, we made our way to this really interesting layer called the marker band, which is this kind of dark layer that you can trace all the way around Mount Sharp. We had no clue what it was from orbit. Was it an ash layer? Was it something different. This is what the marker band looked like when we got here. It kind of looks like a Pohoihoi lava flow, like you might find in Hawaii, but it wasn't. It turns out this is also sedimentary rock, but what is making all of these structures are these ripple features. And there are these symmetric ripples, and when you get on top of it, this is what it looks like. And every single geologist on the team immediately agreed what this was, which is super rare. But what it turns out this is something called wave ripples that formed in a rather shallow body of water, probably just a couple feet deep, as it sloshes back and forth. So kind of like you might find on the shoreline of a lake or if you go to the beach. And this is exactly what we saw here. So this is exciting because it told us that even though we had been in this pretty dry environment, all of a sudden liquid water was back on the surface. And this is some of the best examples that we have in the entire mission of an ice-free lake that interacted with the surface. So what we found is Mars dried up, but it wasn't this sudden dry up. It's this kind of pulse. It gets wet and then dry and then wet and then dry. And so there's a lot of dynamic climate change that was happening in this period of Martian history. Another example of climate change we could see as we came up was this Geddes Vallis channel and Geddes Vallis ridge. This is just a kind of zoom in of what the ridge looks like. It's this big channel that cuts down through a lot of Mount Sharp. Here's Curiosity for scale, by the way. It's this massive, massive pile of rocks. We didn't know what formed it. Was it a dry, just a rock fall that came down the mountain? Was it a river that transported these rocks? Was it kind of a slushy debris flow? We were able to get up to the base of the ridge and see for the first time in a long time, this big contrast. Instead of all of these rocks that were all kind of tan and the same, now we're starting to see a diversity of all different kinds of rocks being brought down from higher on the mountain, all of these black rocks with different textures and sizes. And as we made our way up the ridge and towards the channel part of the ridge, we were able to look at all the diversity and types of rocks. And we actually concluded that, yes, water was involved in bringing some of these down the mountain. And it wasn't just one episode. It was hundreds or thousands of different pulses of water that came. And this would have been something that was one of the last things to happen in the entire history of Mount Sharp because it cross-cuts. It lies on top of all of these other rocks. This is a traverse making our way up the sinuous channel. And this is what it looked like when we actually got into the channel. It's a bit of a busy image, so I'll add some labels here. Here's kind of looking downhill towards that giant ridge that's way bigger than the rover. Here's some of the debris that filled the channel. This is our usual salty unit rocks here. And then something caught our eye as we were actually crossing over the channel were these really weird looking white rocks that didn't look anything like we'd seen before. Here's another view of us as we drove down into the channel. You can see these are little patches that we brushed off with the brush on the end of the rover's arm. But here are these really bizarre white rocks, very distinctive and unlike anything we'd seen before. When we took a closer look at them with our hand lens imager, this is what they look like, a very distinct texture that hopefully you can tell from all those other images I've been showing you. And of course, we're a one-ton rover. We like to break things up to understand what they are. So we drove over one of them. And when we broke it open, we were able to see that the inside was kind of this yellowish material. And when we put our instrument arm actually down on them and were able to assess their composition, we found their composition was pure elemental sulfur, which was, I came in that morning and it was like, what? Wait, no, you mean sulfate, which is something we see all over Mars. And it's, no, this is sulfur. And it was like, wait, that was not on my bingo card. What? So really unexpected finding. This is the only time we found elemental sulfur on Mars. On Earth, you can find sulfur that forms in places like hot spring deposits. A lot of the time, microbes are involved in its formation. We're not in a hot spring deposit here. At least we've seen no other evidence for any high temperature minerals. So we're scratching our heads about how this formed. We have some ideas that are going through peer review right now, but it's a really exciting discovery. Not totally sure what to make of it at this time, but just goes to show you, even 12, 13 years into the mission, we're still discovering one-of-a-kind, first-ever seen things on Mars. This is just, see if it plays, a video that we took. This is as we went into a period called a conjunction when Mars went behind the sun and we can't command the rover. We just let our cameras take some images, and this is a day on Mars and the shadows pass over the sky. I just really like that video. But here is now wrapping back to where we are today at these boxwork structures. This is what they look like from orbit. Again, these kind of big boxes, giant decameter scale fractures that probably formed as groundwater came up 900 meters up the side of the mountain, which is just wild to think about. How did you get groundwater coming up so high to form these resistant ridges and hollows? As we're making our way, I'm just showing a bunch of pictures now, a high-rise picture of Potas mid-drive, but wrapping up, showing our approach to these boxwork structures. This is a late afternoon image. So with the low angle sunlight, you can start to see the relief of them in the distance. And then, of course, this is where we are today. This is now a color picture. Heading down into one of these hollows right here, this little block, to see if we can drill it. Hopefully we can, to understand its composition. And then we'll hop back up onto one of these ridges and drill that and have a really nice paired sample. So I'll just end with a teaser for the road ahead. We're going to continue climbing Mount Sharp. This is a view into the top of the mountain. This is what we call the Yarday unit. These are really enigmatic. We don't know what these rocks are made of. We don't know how they formed. They might be reflective of a whole regional unit that's called the Medusa Fossae Formation that we see other places on Mars and is also super enigmatic. So I'm super excited to keep roaming and get there hopefully one day and figure out what this tells us about an even earlier part in Martian history. And I'll end with our beautiful postcard that we took just a couple weeks ago with our tracks in the distance as we made our way across the boxworks. So thank you very much.